everybody. Thanks for joining this webinar. This is like the first of its kind for us. We're talking today about the shredding-free revolution, and we want to show you how we from Novocycle are redefining the lithium-ion battery recycling sector. And today with me is Fatih. I would say we just do a short introduction about ourselves, like really 1 or 2 sentences. I can't stand it when it's too long. So my name is Taha. I'm the co-founder and CEO of Novocycle. I was mainly involved in electric vehicle sector since around 7 years and focusing also on the batteries and of course of the battery recycling. I think that's enough from me. And Fatih, if you would introduce yourself also, then we can start with the presentation.
Yes, hi everyone, my name is Fatih. I have a background in material science and engineering. Worked a long time for different research institutes, and before Novocycle I was also in pursuit of a PhD in material science. So I've been with this company now since 2021 as a co-founder and CTO.
Great. Okay, so to start with, I will just share a little bit about Novocycle and what is like the impulse and our passion. And this is like Novocycle was incorporated based on innovation in its DNA. So if there is a preconception that we are a recycling company, we are not a recycling company. We are technology providers, and we're providing different solutions across the supply chain of lithium-ion batteries. And our aim is really to making the supply chain of lithium-ion batteries truly circular. Why we're saying truly is because there's a lot of greenwashing, as you know, and we made it to our mission to end this and bring radical transparency to the market. Since 2018, we have been started developing on the recycling process and also looking into weak areas inside of the supply chain to find adaptation potentials for our innovations. I mean, the most recently developed technology, which is now worldwide patented, is our recycling process, where we are recovering 96% of all solid battery materials inside the battery. So we're not only talking about the valuable and critical metals like lithium, nickel, manganese, but we're talking about all the materials like plastics inside the batteries, steel, aluminum, copper. And we're able to achieve a 99.5% purity of active materials, which is enabling them to be immediately reintegrated into the production of new batteries. And there, in December last year, we received a pretty cool update that Fatih will go into more details later on, is that we successfully reintroduced those active materials into a new battery with 100% content. And this battery reached 100% performance looking in the capacity. And we do all of this without using shredding and without producing black mass. So this is really like the important topic here. No shredding, no black mass. It's directly recovering the materials in the original forms. So our approach is we have a multifaceted approach. Of course, we always start with the development of the solutions that we have, and why we are currently updating and optimizing the already developed solutions. We're working on new innovations and continuing with research, as this is part of our DNA, to also look into future technologies. Because as you know, the battery market is evolving and new battery technologies are coming to the market, new chemistries are there. So we need to be already researching the possibilities of recycling of the new battery technologies like sodium-ion batteries, solid-state batteries. So the innovation never stops for us. At the same time, if we want to gain radical transparency, digitalization is a really big topic. So we also need to look into the collection of data and also into the improvement of the visibility and the knowledge for battery technologies. And of course, we cannot do it alone. If we want to have a bright future and a more sustainable future for our children and the generations in the future, we need to do it together. So this is not a one-man show. This is a collaboration-based topic. So we're always looking into collaborating with universities, with other industry players, and this is really important for us. and why we're doing this, and we're focusing on making real impact. We're always looking for environmental responsibility, but environmental responsibility alone is not enough to maintain a business and also to maintain the market and economy. We also need to look into economical feasibility. So all we do is really looking into high innovative technologies that at the same time bringing more sustainability and more circularity, but also bringing an economical feasibility, which makes it interesting for our customers to implement those technologies. Now let's go into a little bit of data, a little bit about information about the lithium-ion battery sector. As you all know, the battery demand projection for the next years is really impressive. The battery demand in the next years, only looking into the electric vehicles, will be triple until 2030. And after 2030, we will have a double number for the demand of the batteries until 2050. Of course, with this demand, we're always talking about raw materials and necessary sources in order to get those raw materials out. So there we will face a huge supply-demand discrepancy, where the supply will face a shortage in order to deliver critical materials like lithium, like cobalt, like nickel. And as you know, nickel and cobalt especially are not only used for batteries, but also used in the metal industry. So we will face a clash about these materials in the near future. Of course, there are new developments where now a lot of companies are targeting cobalt-free and nickel-free battery materials as the chemistries, and also solid states. And also we're now seeing more and more companies looking into even replace lithium by sodium with the sodium-ion battery technology. So we need to always keep being updated also on the focus of the recycling sector. And of course, all this has also environmental implications. Lithium-ion batteries are not zero neutral. They have also their issues. Of course, they're a good step during the electrification to change from internal combustion engines to electric-based engines. But there's still an environmental impact that needs to be reduced. And doing the recycling, we're centralized shredding facilities is not really the best way to do it. One, because we're having a lot of material losses, which are not always communicated, and we will come to that later. But two, centralizing recycling facilities and transporting the batteries that are needed to be recycled over thousands of kilometers doesn't help to reduce the carbon footprint. And the number 4 of the important topics is the governmental regulations. So as you might know, there is a new EU battery regulation, which is focusing on recycling efficiency and also until 2031 implementing minimum quotas of recycled content into the production of new batteries. So all of these topics are giving us the necessity to recycle those materials at a high yield, and this should be the focus. Because the market, how it's going today, and now this is like, I want to really bring a bright light onto this and speak a little bit about the truth, which is not always communicated the right way. So you always need to listen to the words that are put in there. So the world, how it's gone today, is that all kinds of batteries are entering the shredding process. So these batteries got shredded and crushed into something called black mass. The black mass is always quoted as the new gold. But unfortunately, it is not really communicated right. So yes, the black mass contains critical materials like lithium, cobalt, and manganese, but also contains a lot of impurities. So going to the black mass, we already have a material loss of around up to 40%, depending on the recycling process and on the purification steps that there is. But at the same time, going then from the black mass to the critical raw materials, we're removing residues of graphite, of copper, of aluminum, whereas another additional material loss, and also a high complexity in the chemical processing, which is increasing the costs and decreasing the economical feasibility. So you always will hear sentences like, in our process, we're able to recover valuable metals up to 95% from the battery's black mass. But what does that really mean? Is on the left side, you can see a picture of a shredding process producing black mass that has not a really good purifying process, because as you can see, it is a little bit rockish. That means that the binders and electrolytes are not really well removed in this process. Of course, there are more advanced processes by now, but these binders, when they dry, they make the whole mass rockish. That leads to a high complexity for the chemical processing afterwards. And on the right side, you can see an average composition of this black mass, where you can see that the valuable metals quoted in the quoted in the above sentence, made by a recycling company, the content there is 27%. The rest is all residues that need to be removed. So we're talking about 95% that can be recovered from the black mass, but this 95% is basically 95% of this 27%. So overall, we're talking about 25% max that can be recovered from the original battery that we have. And we from Novocycle, and after this slide, I will hand over to Fatih to share some more details with you. We focused on how can we ensure the highest purity of the materials and the lowest chemical complexity in order to also ease our environmental permit processes for our customers when we supply this technology. For us, it is really crucial that in the first steps, when the end-of-life batteries enter our process, we're doing a diagnosis of each battery cell and analyze if this battery cell still has a capacity of over 75%. This is for us the critical capacity in order to enable them to go to a second life process in a stationary energy storage, because there they can live for 2 to 3 years longer, because the stress on the battery cell in a stationary energy storage is not that high. So there we work with partners and also have our own solutions to go for a second life application. If the capacities are below 75%, then the batteries enter our recycling process. When the first step, we discharge the batteries in order to deactivate the batteries so that they do not explode when we're handling them. But at the same time, with the discharging, we're collecting all the lithium on the cathode side to have a selective recovery of the lithium at the end of the process. In the third step, after the discharging, we're dismantling the battery cells. So we're now going into the dangerous zone where we're opening the battery cells and separating the anode, the cathode, and the separator from each other. And this is done automatically with an own developed machine that is able to do that in a safely manner so that no operator has any involvement into this process step. The metal scraps and the mixed plastic coming out of this process are going to different recycling streams, to metal recyclers and plastic recyclers. The cathode, the anode, they're entering a gasification process in order to remove the electrolytes and binders, after which we can separate the active materials from the collector foils. So at the end, we have high purity cathode active material recovered and high purity anode active material recovered. And the separators are entering a washing process, and after that, going into the separate plastic recycling stream. And with that, I would hand over to Fatih to share a little bit more details about the material compositions.
Okay, thank you very much. So I think in the next few slides, we'll compare a few of the results that we can show at this moment. So definitely on this slide, we see on the left side the material composition of our recovered cathode materials. And as you can see, like the nickel, cobalt, lithium, manganese, they are recovered in oxide composition. So we don't destroy the microstructural structure or even the composition that much. And the low impurity, which is about 0.5%, which consists of phosphor, copper, iron, sodium, and other trace materials. And usually with another short step, we can even increase the purity up to 99.9%. So a lot of those materials can be removed very easily. So in total, we can summarize, like with the technology that we are providing to this day, that at Novocycle we can recover more than 96% of the solid materials with a high purity, so above 99%, compared to on the right side, it was also shown previously, like the valuable material composition within the black mass is only maximum about 27%, and this needs then to be run through a chemical process to really get rid of further impurification. So the organic compounds are not listed here. Usually the binders or the electrolytes, they are still present in the black mass, and they definitely need to be extracted. So there's a lot of post-processing required if we go to shredding and black mass. However, if we do like this dismantling route that we're proposing, we can really directly reuse the material as it's extracted from the electrodes. So we can go to the next slide. And what we did, especially also on the anode side, it's again the same results or similar results. Here in this batch, there was the impurity level a bit more higher, but usually the purity is around 99 to 100%. So I think on the next slide, there's also an example showing it. So here we can see again, with the dismantling route, we can recover up to 96% of the valuable anode materials with a high purity as well, so 97 to 100%. And this material, so both the cathode and the anode materials from the purification standards, they can be reused for battery manufacturing, and that's what we did with our partners. So also there are some SEMs here. We can see that there are a lot of spherical particles, but as a case study, what we did is we partnered up with some e-scooter companies. So we got their scooter batteries, and so just from the material flow, we dismantled the modules and we recycled the cells, and we recovered the cathode and anode materials via dismantling and our different processes. And we see the composition on top from the cathode materials, so there's almost no impurity. So again, we have the NMC structure, we have the particle size distributions, and on the bottom right, we see like the graphite, which was extracted in this case study. It was only graphite materials or carbon materials, and the particle size distribution from the initial state, it was very uniform. So we assessed that this material can be used for battery manufacturing. And what we also did is within this case study, we recreated or remodeled the battery module from the scooter. We looked at all the state of health characteristics of the different cells. So we analyzed the cell position. So there's a lot of research that we also do and information that we're collecting. But I think the next slide is a bit more interesting. So we took the anode from different batches. So we had actually 3 test cases. I think the third one is not here. So there's a production scrap, different mixtures, and just end-of-life batteries. And the usual trend with the material that we recovered. So on the left side, we see a half cell test with the recovered or recycled anode material in a C10 test. And we see that the initial capacity reached up to 350 milliampere hours per gram, which is quite comparable to virgin anode materials. And on the right side, we see a full cell test in the combination with NMC 811, and that will reach an initial capacity of more than 186 milliampere hours per gram. And in both cases, we had a cycle life of more than 500 cycles above a performance of 80%. So these are major successes for us. So, and we tested this also for production scrap for the combination shown here as test case 2, but also for end-of-life batteries. And they all had the similar performances. So it was always between 96 to 100% compared to virgin materials. And then I think I'm handing over to Taha again.
Okay, thank you, Fatih. First of all, what I need to say is this is like a really big effort from our team, and I'm really proud that we have these results. Also for Fatih, and also with the collaboration partners with who we did that. It was really great to see how fast we can reintegrate those materials, and also like without any further postponement of the process steps. So this is really a good thing. But looking into the results that we have is summarizing everything. We do not shred or do not create black mass formation. So all we do is non-destructive methods to recover the materials in the pure form, which is leading to a high purity output, which is pretty important in order to also gain profitability from an economical perspective. Because while black mass is treated currently at around $4,000 to $5,000 per ton, we have the active materials and the purity levels that we have that can be sold for 5 times the price of the black mass. And then at the same time, reducing the process costs of all of these things is enabling us to really gain profitability for our customers where we are providing these technologies. We're one of the first and currently only recycling technologies that can recover more than 96% of the anodes, because we are doing the separation in the pre-processing already. And we've proven the reusability of the recycled materials, which is ensuring sustainability. And one of the next steps also will be to analyze how often can we cycle those things, like how often can those materials be recycled at the end. And this will show us how far can we go for the reduction of the dependency of third-party deliveries and third-party countries. And then, I mean, what is up in the future? Right now, all we did was recycling. So taking the batteries on the materials out of the batteries and putting them back into batteries. And the next steps will be to really work on projects where we're taking out the materials and putting them into different applications, which then will be really an upcycling process where we take it from a lower environment and put it into a higher complex environment. And with that, we were paving the way towards the sustainability. And with that, we're also looking into how to expand the battery material lifespan. And yes, we're looking into collaborations with that. So we're always open to work together with universities. So if you have an interest in collaborating in these topics, always feel free to reach out to me or Fatih. Yes. And with that, I think we can open the stage for the Q&A. So a question from Alex Sargent. Hi, both. Interesting presentation. Thank you very much, Alex. On slide 8, you mentioned you discharge your batteries. I was wondering what technique you used to do this and whether the discharge was to 0 volt or 0% state of charge. Fatih, I will give that one to you.
It's like the discharging is a dry discharging process. So it's a combination of constant current and constant voltage. The initial, so it's a deep discharge. We target 0 volt, but we don't go really down to 0 volt. And there is some rest state of charge. So we are not really completely doing a deep discharge, but there's an intermediate process. So just to get rid of the first high resistance, and then doing it's a multi-step discharging process that we have. So with that, we can reduce the discharging time, so the total discharging time. So it's like with high power and then reducing the current levels. And with that, we can reduce it almost to 50% of the usual discharging time.
I hope that answered your question, Alex. Going to the next question from Beatrice. It's a question about the actual process to extract the active material. When we speak about the gasification step, what does that exactly entail? So the gasification process, I mean, Fatih, if you like, you can answer it.
Yes, sure. So the gasification process, we use a different term because it's always confusing with pyrometallurgy and pyrolysis. So different environments, it's a thermal treatment at different environments, which allow us to stepwise to recover also the electrolyte, but also to it's at a more let's say material friendly environment. So with this gasification process, how we stated, we can remove the electrolyte and binding agent so that we can then separate the active material from the foils. But at the same time, we're not destroying the microstructure of the material, so it stays in the crystalline form. The particle sizes stay the same, so they don't grow or shrink or something like that. So it's the combination of different process parameters and process conditions that enable us to remove the active material from the foils.
Hope that answered your question, Beatrice. Ravindra is asking if we recover carbon materials also. Yes, we're recovering the carbon materials as well. Emirjan is asking if we use a hydrometallurgical process, so can we recover metals one by one? I will shortly answer that. We're using the entire dry processing to recover the active materials in the original forms. So as shown by Fatih, we're recovering the compositions as they are. So if we're entering NMC 811, then we get a material at the end that has a similar structure. So there's currently no need for a chemical process for the production scraps. But for the end of life versions, there is a degradation that we can see. So for them, we will need a hydrometallurgical process step. But even there, we're looking more into co-precipitation rather than extracting selectively the materials, because currently in the market, this is a process step that is not economical feasible. When we reach a market where there's different materials that we need, for example, new compositions are necessary, then it would make sense to selectively extract the nickel, the lithium, the manganese, and the cobalt, and then we would go for a selective extraction. Hope that answers your question. Mariam is asking very impressive results. Thank you very much, Mariam. Practical question about the difference in cost of recycling via black mass and innovative. Is it cheaper or more expensive? It's way cheaper. So, Mariam, if we look at a ton base, then we're looking into 1/3 of the cost per ton of material recovered and also introduced. This is based in 2 topics. One of the topics is that we reduce the process steps from over 20 to only 10 to 11 process steps. And at the same time, the energy consumption that we have in our process is also pretty much lower than the energy consumption for shredding-based processes, because we do not use heavy processings. So we're really asset light and capex light in that topic. Next question is from Bill. Great concept, all the best. What is the TRL level? The TRL level right now is 7. So we have an operating facility in Istanbul, and we're right now in the phase of opening the next facility in Europe as well. But of course, we need to further improve the automation. So the next steps would be to increase the automation of the process steps. And at the same time, Fatih and his team is looking into improving the chemical recovery and also looking into building new active materials based on secondary materials. What is the elemental measurement method, EDS or ICP OES? Is it done at gram or kilogram scale? Industry requirements are in kilogram. Fatih, you can answer that. I think this is more like your question. How do we measure the elements?
So we're doing both. So EDS and ICP. So EDS is definitely in grams, and ICP is also currently in grams. But currently we're collecting different bigger batches on a kilogram basis and taking different samples from them. So on the elemental measurement, it will be both EDS and ICP.
Yes. Emirjan is asking if we're trying to recover different types of batteries, LFP, NCA. Yes, since we're not going to the chemical processing and we're not destroying the structures, LFP recovery is possible, and NCA is also recovered already. We're also looking into NMC, different types of NMCs, 811, 111, 611. NCA was done, LFP, and also LCO structures were recovered, Emirjan. Alex answered my question perfectly. That makes me happy. On the note of discharge, if you're going to close to 0 volt, I was wondering if you saw any contamination from over discharging the battery. For instance, copper dissolution on the graphite. Slide 12 showed 100% carbon composition. But I would hand over this to your side.
So our copper contamination comes mainly from the separation step of the active material from the graphite removal from the copper foil. So there we have sometimes a impurity level between 0.1 to 0.2%. But at the moment, we did not encounter any copper contamination within the graphite due to discharging.
Yes, I'll go to the chat because there are also some questions. So thanks for the people that copied the questions to the Q&A. One question from Istvan is, do we share a link to the recording as well? Yes, you will get a recording of this session. What kind of hydrometallurgical processes do we use? TRL level was answered. So hydrometallurgical process that answered before is we're using organic acids since there is no high impurity. So there's low impurities in the materials. So we're able to use more non-hazardous acids and organic acids to recover the materials, but also there we're looking into further improve the hydrometallurgical recycling. But right now in the TRL level we have, there is no need for production scrap to do the chemical processing. For end of life, there is a need for it, but also there is, if you reduce the content of recovered elements, like Fatih showed a page where we reintroduce 45% of end-of-life materials into the battery, and even there it showed near 100% performance. So we're currently questioning if the chemical process is really needed in order to reintroduce those materials, because we believe that the chemical processing is only needed if you want to try to build new active materials out of it. So currently, to answer the second question as well, we don't need any water in our process right now. The electricity requirement of the process is around 15 kilowatt hours per ton. I think per ton. No, it's 150 kilowatt hours per ton. To answer that question as well. I think we don't have, or we have questions. Yes, Alex is thanking you, Fatih, for the answer. Okay, so right now that was it. Any further questions?
I can ask you, what are the next steps of Novocycle?
Well, okay, thanks for the question. Okay, answer Fatih's question. So the next steps for Novocycle is really to further improve the automation level of the facilities, because we want to reduce the dangerousness of the entire process. So reduce the involvement of human labor in terms and the toxic environment. So that is why we automated the dismantling, for example, and now we also further will automate the whole material separation and the intralogistics of the processes. And after that, it will be about expansion and really building a decentralized recycling corridor, but we also look into digitalization topics to build a database for batteries, because this is one of the biggest topics for us. When we receive the batteries, there is no information, or at 80% in the cases, there is no information about the battery cells that we receive. And based on that, we want to partner up with different companies and do our own database as well, to make that one transparent, in order to have like really good information about the battery cell chemistries, about the composition of the cells in a database, and then provide that via a platform for our customers so that they can go in there and can analyze different kind of the battery chemistries. Emirjan is asking, it is very possible for lithium to be lost in the products you recycle. Have you encountered such a problem? Are you using it in applications where capacity is lower? I think that one was also answered. We are doing the discharging not only to avoid the explosion, but also to collect all the lithium on the cathode side. So we're localizing the lithium on the cathode. And since we're not shredding or crushing or do no wet discharging or have no water involvement, we recover almost 100% of the lithium. So we're at around 95%, Fatih, something like that, for the lithium recovery of the original levels.
Yeah, I can also do in addition to that. So the lithium recovery rate, or the content of the lithium that we're recovering, is always between 6.5 to 7%. So which is almost the same that is inputted or added to the cells. So from the lithium salts and stuff like that. We did different analysis, and we saw that within the separator foil, or even on the anode, that the lithium content there is less than 0.1%, or even low. It was in the ppb range. So from that assessment, we just go that the majority of the lithium has to be at the cathode side, because there was no other place for the impurity or for the lithium loss that we could encounter at the moment.
Hope that answered your question, Emirjan. Beatrice has another question. The capacity of the facility so far. So we have one manual acting facility which is running at around 20 tons, which is pretty low, but we improved that with the automation. The second one that we have right now is running at 200 tons. The one we built in Europe has a targeted capacity of 500 tons. And the sweet spot where we're trying to achieve with the full automation of the process is 1,000 tons, Beatrice, because we don't want to go above that, because our strategy is really that we build decentralized facilities wherever the waste is. So the waste should not come to the facility should come to the waste. And this is our main strategy, because the biggest cost point in the process is the transportation. So by just avoiding the transportation, we're also cutting the transportation costs, which is again increasing the profitability of the facilities. And you can think of our facilities that once we have 1,000-ton facility, the biggest size that the facility will have is 1,000 square meters. So it is really a small space that we need in order to build these capacities. Last question from Emirjan, maybe last, maybe not. How much longer does the process you do instead of shredding take? Compare both of it, if you go from a ton level, since we reduced all the processes and you directly reach the active materials, we can say that the time of reaching the active materials is much shorter. We're removing 7 to 8 chemical process steps, which are running at hours, and we directly reach the active materials, so we're pretty much faster. Of course, the throughput to produce black mass is one thing, and then from the black mass to reach the active materials is another process step. Of course, in shredding, to do the production of black mass is much faster. You can handle tons in minutes, but the really critical issue, Emirjan, is from reaching from black mass to the active materials, and this part we just have in one stream. You'll reach the active materials, so it is much faster. How do we handle the cell-to-cell variation, which is not an issue in case of black mass method? There are 3 different cell types, as you know. We have cylindrical, prismatical, and pouch cells. So each of these cells enter a different process step of the dismantling. And then it's really good on our side that we don't need to think much about the chemicals inside of it. So it is more like an automation of the dismantling, where we have 3 different automation types targeted, where each of the automation cell types will be able to handle different size. For example, the automated machine of our cylindrical cells is based on a module which has, or shuttle, which has a placement for example, 15 battery cells, 18650. And then we also just need a shuttle for the 21700 and the shuttle for the 4680. So this is all handled. With the black mass method, yes, you're right, you just can throw the modules in, but based on that, the impurity level is so high, so you always need to think about purity and yield and profitability of the battery material value versus capacity. So it's always about capacity, purity. And if you go for the purity and reach high capacities, this is the sweet spot where you should operate. Chat, maximum capacity of our technology. Will you buy back the output? Okay, maximum capacity that we're targeting is 1,000 tons. Right now we're at 200 tons per annum. The buyback of the output is, we're trying to build a platform, because we have trading partners, in order for our customers to be able to directly sell their outputs to those material traders. And yes, we also ourselves are doing research, but the amounts that we buy back are pretty low. So it is more that we built the trading system, or we built the relationships with the material traders for you, in order for you to be able to sell those materials to them. Curious on how end of life, where the batteries, the lithium percentage tests were done on. So I think this is like how were the lithium percentage tests done on the end of life batteries, Fatih?
Yeah, I'm not sure if it's a faceted question. So definitely we did state of health checks on different cells, and we analyzed the lithium percentage. So from state of health about 98% down to 60%. But I'm not quite sure about the numbers. But usually it was the initial lithium percentage. How we tested is that we opened the cells manually in an enclosed environment, so in a glove box under special environment. We took out the cathode and the cathode sample, and it was then sent to the ICP, where most likely inorganic solutions were used for the lithium quantity test in the ICP mainly. Yeah.
Good. Great. Thank you very much for all these interesting questions. Really like it. Any further questions? If not, we reached the end of the meeting, so we have time for 1-2 more questions. If that was it, I think that was it. So thank you really much. Thanks for the participation. I hope that this new horizons could show you what is possible with direct recycling on a dry base. And if you have any questions, let me also share this. If you have any questions, please feel free to contact hello@novocycle.com. This mail address was especially done for this webinar. So every question and every remark that is entering this email address will reach me or Fatih. And then we will answer all your questions afterwards, or your rows. And also feel free to visit our website on novocycle.com. And you can recycle a battery on our website by scrolling down. Might be a funny gag. Thank you very much. It was really interesting for me. And Fatih, if you have last words, and after that I would stop the webinar.
Like you mentioned, thank you guys for being here today. Thank you very much for the great questions. And if you have any other questions, just hit us up on the email. We will try to come back to you guys as soon as possible, and most likely also add some new content or additions on the webpage as well.